I think it's obviously a very exciting time in the field, especially as the rate of new discoveries is increasing so rapidly. And this is really kind of, pushing us to change how we think about FRBs and ultimately what could be powering them. And now that we're moving into this regime where we can obtain host galaxy associations, this will really be key in terms of understanding their progenitors. And so what I want to do today is contextualize that a little bit and describe how the host galaxy demographics and the positions of FRBs within their host galaxies can inform us about the progenitors. And so this is an area that historically has proven to be quite useful in terms of understanding the progenitors of various types of different transients. In that, of course, the properties of the galaxies and how they're spatially distributed within these galaxies tells us about the environments that can produce these events. And so similarly with FRBs, I think understanding their host and local environments, as well as whether or not the properties of the events themselves are in any way correlated with their environments, will really be key to making progress. So stepping back for a moment to talk about how we can localize events. So generally speaking, this is done in one of two ways. The first is, of course, via the direct detection of events using interferometers. So as we saw first with the VLA, now with ASCAP, DSA, and the EVN. And then there's indirect localization via the detection of longer duration multi-wavelength counterparts. But as we've seen, this sort of direct localization has been the more successful path thus far, I think particularly while we don't really understand the range of multi-wavelength counterparts. And so I think it's worth assessing sort of where we are today in terms of localization capabilities. So here I'm showing on the y-axis the apparent magnitude of a galaxy as a function of the localization region. And this is essentially quantifying how likely it is for a source to be in your field purely by chance. And so this is just parameterized using galaxy number counts. And then the size of your region is parameterized in one of two ways. So either based purely on the area of your localization, or for much smaller scales, so really in this sort of sub-arc-second regime, the dominant scale becomes either the size of the galaxy or the offset between the FRB and the galaxy. And that's what's defining this plateau here. And you can also imagine that, especially as you go to higher and higher redshifts and these sources become more and more faint, localizations really at the level of subarc seconds are what we'll need. And this is really the regime of interferometers. And so this is all borne out by existing observations. So here, and for this talk, I'm going to focus on the published events. And so these are sort of rough positions for the localizations that we have today. Yeah, so that just sort of shows the regime that we're in now. But what I want to do next is give a brief overview of these published events that we have, so sort of talk about the properties of each of their hosts. And then we can step back and sort of look at them in the context of, for example, other host transients, and sort of look at them as a population of sources. All right, so starting with the first repeating FRB. This, of course, was precisely localized due to the repeating nature of the event, which allowed for this unambiguous host identification with a low luminosity dwarf galaxy at a redshift of about 0.2. And I think this, the fact that this was a low luminosity dwarf type galaxy was really surprising and perhaps unexpected. So these types of galaxies account for less than a few % of the total stellar mass in the local universe. And so in other words, if we think that the FRB rate tracks the stellar mass or the star formation rate density, this is a really unusual host. The actual position of the FRB was resolved to this bright star-forming region. And this, of course, was used to invoke a possible connection between superluminous supernovae and long GRBs, so these two classes of transients that occur preferentially in these types of galaxies. And in fact, the irregular morphologies that we see from these galaxies, from the hosts of both of these transients, is really consistent with what was seen from the repeater. So again, this is sort of hinting at this possible evolutionary link between these types of events. All right, so the overall picture changed somewhat with the ASCAP localization of 1809-24. This is a sub-arc second localization to a massive lenticular or early type spiral galaxy at a redshift of about 0.3. So now we're beginning to push further out in distance. And as we can see, the position of the FRB is spatially offset by about 4 kiloparsecs from the center of its galaxy. And so it is similar to the repeater in that respect, that it has this offset. But overall, the properties of the galaxy point to a generally older stellar population with a declining star formation rate history and a low current star formation rate. And unlike the host of the repeater, this is a much more massive galaxy. In fact, these types of galaxies account for the majority of stars in the local universe. And so this could be perhaps suggesting that not all FRB progenitors require special conditions. And in fact, this was the motivation for recent work by Ben, Brian, and Ito, showing that this particular host galaxy is actually consistent with the properties of the host galaxies of short gamma ray bursts. And so this is, again, one example where the properties of the host galaxies can sort of inform our understanding of FRB progenitors. All right, so moving on to FRB 1905-23. This was localized by the Deep Synoptic Array to a position a few arc seconds in size. And so this outer contour here corresponds to the 99% containment region. I should say they're able to rule out the possibility of a dwarf galaxy in the region out to a redshift of about 0.45. And instead, the presumed host here has a redshift of about 0.6. So this is consistent with the expected IGM contribution and also makes this the furthest FRB host to date, again, that's published. The total stellar mass is significantly higher, while the specific star formation rate is lower than the repeater. And so again, this is suggesting that massive star progenitors may not be required for the production of FRBs. And similarly, the fact that for this particular event, the host galaxy is probably not contributing a lot to the DM, suggests that these events may not need to occur in regions of active star formation. So this host is really a lot more similar to FRB 1809-24, which I just talked about, which is generally a much more massive galaxy with little active star formation. And so again, this suggests that perhaps some progenitors come from an older stellar population. All right, so following that event, there was the localization of FRB 1905-23. I have my numbers wrong, 1811-12. Excuse me. So this time the host galaxy was identified as a blue intermediate mass star-forming galaxy, this time at a redshift of about 0.48. So again, we're starting to push further out in distance. It is a lower metallicity galaxy, so consistent with its lower stellar mass. But given its larger mass relative to the host of the first repeater, this is starting to suggest that perhaps dwarf galaxies are not the dominant hosts of FRBs. All right, so just to step back for a moment. So we have here 3 apparently non-repeating events at this point localized to non-dwarf hosts, and we have the 1 repeater localized to a dwarf galaxy. And so one might conclude that there is this apparent dichotomy between repeating and non-repeating events. But of course, the story is not quite so simple, and so the overall picture again changed with the recent localization of the Chyme Repeater. So this is a sub-arc second localization of the repeating FRB 1809-16, and it was localized with the EVN to milli-arc second precision. And what was really interesting, well, first I should point out that it is the nearest localized event to date. But what was really interesting about this event was that it was localized on the outskirts of a massive spiral galaxy to this V-shaped clump here, so associated with some region of star formation. Relative to the first repeater, it's much more massive. And it has a metallicity about 5 times higher. So overall, this is much more analogous to the Milky Way galaxy. And so, as I said, it had this, association with the V-shaped clump. This could be evidence for some kind of interaction, possibly with a dwarf companion. And so, I will say that although the host is very different from the first repeater on this sort of galactic scale, the fact that it is coincident with a star-forming region suggests that there is a consistency, at least for the repeating events thus far.
Is that the metallicity of the core of the galaxy or the location of the FRB?
I believe that metallicity is quoted for the FRB location, but someone... It is the core? Okay, so then the star formation rate, metallicity are all quoted for the core, correct? Okay, yeah.
You can barely determine it at the position of the FRB. It's much harder. But the metallicity was for the core of the galaxy.
Use your seat mic, please.
The metallicity was for the core of the galaxy. The star formation rate, we have quoted it, but it's because the slit was only 2 arcseconds, it doesn't incorporate all the light from the galaxy.
Yeah, so that's why it's a lower limit there.
Yeah.
Okay. Okay, so that's just an overview of the published events to date, those that have host galaxy identifications. But now what we can do is sort of take a step back and look at these events as a population of sources, as I said, and see whether or not a cohesive picture starts to emerge. So one can, for example, look at the star-forming main sequence. This characterizes the relationship between the star formation rate and the stellar mass of a galaxy. And so Ryan showed this plot yesterday, and I think it included the latest ASCAP events. But here again, I'm plotting what's published. And this really just illustrates that the hosts thus far sort of exhibit a range of stellar masses. I should point out these two events here are upper limits on the star formation rate. And again, for the second repeater, this is really a lower limit and doesn't reflect the global star formation rate. And so similarly, we can compare the properties of the hosts to the host galaxies of known transients. So here I'm showing a mass metallicity diagram for a few different types of transients. We can see that superluminous supernovae and long GRBs occupy this region of the diagram here, corresponding to, of course, low metallicity, low mass galaxies. Core-collapsed supernovae, on the other hand, sit in this region here. And that's because they tend to track the formation of stars. And so in principle, the fact that these events here in this region correspond in low metallicity environments is likely telling us something about their formation. And so one example of this is magnetars powering superluminous supernovae. And so in this case, the low metallicities are required in order to sustain sufficiently high angular momentum. If the metallicity is too high, this would lead to increased mass loss through stellar winds. And so again, this is just an example of how the environments should really be informing, I think, our progenitor models. So we can compare to our sample of FRB hosts. And so we see, of course, the repeater falls here. The second repeating FRB lies in this region here. So really in contrast with the first one. And then for the remaining events, I'm really just plotting the stellar masses here in cases where I couldn't find precise values for the metallicity. But immediately that we can see that these two events are likely consistent with this region here of large stellar masses and metallicities, where I do believe there is indication for this event that it's a generally lower metallicity galaxy. And so immediately this question emerges, and it's worth thinking about what could be driving this apparent dichotomy between the host galaxies. And are there, for example, other properties of the FRBs that might inform us as to why this is happening? So short GRBs will definitely span a range of masses, I believe. I see, so these curves here. All right, so another thing that's commonly explored when it comes to transient host galaxies is the offset distribution. And so similarly for FRBs where we have really precise localizations, so probably at the level of subarc seconds, we can compare their positions within the host galaxies to the expectations for other types of transients. And so this should tell us again about the conditions and therefore allowed range of systems that could produce FRBs. So here I'm comparing just the three events with really precise localizations to the distributions for both long and short GRBs and also superluminous supernovae. We can see that for 121102, the somewhat smaller offset is really more consistent with the superluminous supernovae long GRB population. And it's also consistent with the fact that those events tend to occur in bright UV regions of their host galaxies with generally small spatial offsets. And conversely, because neutron stars can experience these large natal kicks, they can exhibit a large range of spatial offsets. And so that's why for short GRBs, so these two events here may be more consistent with the distribution for short GRBs, for example. And so we can play the same game and look at the distribution of stellar masses and star formation rates. Here, I should say I'm also including the distribution for type 1a supernovae, since these are believed to be a sufficient proxy for the accretion-induced collapse of white dwarfs. And Ben mentioned this yesterday as another possible channel for these more longer-lived magnetars that might produce FRBs. And what we find for the stellar masses is that aside from the repeater, the generally larger masses are sort of inconsistent with the distribution for superluminous supernovae. And so this is at least suggesting that superluminous supernovae are probably not the dominant formation channel for FRBs. I think the picture is sort of less clear when we look at the star formation rates, especially because we're dealing with limits in a few cases. But one can imagine that as we build our sample of localized events, we can start to play these games where we look at the distributions as a population and compare to what we see for other types of transients. Of course, it's very small number statistics at this point, so I wouldn't draw too many conclusions from these plots. All right, so that's kind of looking at the properties of the hosts as a whole. But one thing we can do is sort of invert the problem. Excuse me, and ask what the host galaxy demographics should look like for various formation channels. And so this is an exercise from Nickel et al. 2017. And the idea is that for a given formation channel, given the expected fraction that should occur in dwarf and massive galaxies, one can ask how likely it is to localize an FRB to a massive host as more and more events are localized. And so this was done by simulating 10 FRB localizations with the host galaxies essentially randomly drawn from the expected fraction that should occur in dwarf and massive galaxies for each channel. So for example, and so I've listed those down here. And so for example, with short GRBs, roughly 38% reside in less massive galaxies than this threshold to find here. While superluminous supernovae, on the other hand, again, occur predominantly in these lower mass galaxies. And so the idea is we can repeat this process many times, simulating the FRB localizations to find the cumulative probability distribution of finding a massive FRB host as more and more events are localized. And so this is what that looks like. So each curve here depicts the probability, as I said, of finding a massive host as more and more events are localized. So for these different formation channels listed here. And so for example, this red curve up top, which characterizes the short GRBs, is essentially stating that 3 localizations in exclusively dwarf galaxies could rule out a channel in which short gamma ray bursts are the dominant production mechanism. Of course, if we look at where we are today, we're seeing a bit of a different picture. And so what this is telling us, for example, so this curve here is tracking superluminous supernovae, and it seems to be inconsistent with that. So again, this is sort of more pointing towards this idea that superluminous supernovae are probably not dominating the FRB rate. In other words, I should say that we can't rule out a scenario in which superluminous supernovae are at least contributing to that rate. It also could be that the FRB rate is tracking the stellar mass. Yes.
Define dominated, like what threshold are we talking?
Yeah, I'm not sure I could quantify that.
75%?
Yeah, I mean, I guess out of the 5 events, we have one whose mass is consistent, for example, with a superluminous supernovae host, so 80%. Yeah.
I think the orange line is superluminous supernovae are 90% and 10% are short GRB.
Oh, is it?
Yeah.
Okay.
So it still.
So it still could be a large fraction, yeah. Yeah, so I guess the other thing I think that stands out to me is the mass distributions and the fact that, they're all sort of at the very tail end in terms of superluminous supernovae masses. But the idea is that, we should be able to look at the fraction of these various types of transients, their occupation fraction, and assess sort of what channels are allowed and not allowed. All right, but that's all I want to say about the larger galactic scale environments of FRBs. And so switching gears a little bit, I want to talk briefly about the more local environments. And so, of course, the first repeating FRB was coincident with a persistent radio source. And this, of course, led to a number of models describing the emission in the context of a magnetar nebula. We've heard a lot about them over the last couple days. And so I won't really go into detail. But I will say for a long time, or at least until we had a few more host localizations, this persistent radio source, especially in the context of the magnetar models, led to the idea that perhaps quiescent radio sources from FRBs are more ubiquitous. And that's not really what we've seen thus far. And so here I'm plotting the various radial limits for the events with hosts as a function of their spatial offsets from their host galaxy centers. We can see that in a couple of cases, we're sort of probing the similar level of the repeater's flux density. 1905-23 really isn't as constraining. And then, of course, for the second repeater, we have this limit that is well below the first repeater's flux. So this rules out the presence of a source similar to what we saw from the repeater. But that being said, as discussed in the 1809-16 paper, you can have a system that's much older than 121102 that's consistent with what we're seeing here. And so a flux decline at this level wouldn't be really unprecedented if you just invoke a much older source age. And in fact, this is also consistent with the lower observed RM when compared to the repeater. And also the fact that the isotropic equivalent energies of this event are far less energetic than the weakest burst that we've seen from the repeater. And so this could be maybe pointing to some difference in the engines, or again, perhaps the ages of the systems. And this is the point that Ben made in his talk yesterday, showing how a magnetar nebula might evolve over time, and how such differences aren't entirely unprecedented. But really the point I want to make here is that I think it's too early to rule out the presence of radio sources, given that we don't really know the full range of radial luminosities. Okay, so for the last part of my talk, I want to spend some time talking about what are more targeted searches for FRBs, based on what we've learned about their environments thus far. So there was some discussion about this yesterday, but really I think it's worth thinking about, and hopefully we'll be able to talk about it more in the discussion section. Because I really just want to emphasize that even though we're in this regime where we can obtain these direct localizations, if we were able to detect an FRB in this way, it would lead to immediate knowledge of the progenitor. And so I still think these searches are really useful. And particularly motivated by the first repeater, there have been a lot of searches looking for FRBs from the locations of superluminous supernovae and long GRBs. I've just listed a few of them there. Casey published his work with collaborators last year. And so, again, I think that obviously these are very challenging. If you don't detect an FRB, it doesn't tell you that these events don't produce FRBs. But nevertheless, I do think these are important searches, and I think we should be thinking about similar types of searches that we can conduct. And so I just want to briefly say a few things about one of the discoveries that came out of our survey. So this is the Superluminous Supernova PTF-10HGI nearly 8 years post-explosion. And what we find is a persistent radio source coincident with the supernova position to within about 0.1 arcseconds. I should also point out that this source is not detected in our ALMA 100 gigahertz observation, nor do we detect any FRBs within about 40 minutes of phased VLA observations. Although we are in the process of analyzing about 15 hours of Arecibo observations. And so what we show in our paper is that while a star formation or AGN origin is unlikely, instead what we could be seeing is evidence for a central engine. And of course, this could be due to either a magnetar wind nebula or an off-axis LGRB afterglow. And so here I'm just showing representative models that are consistent with the observed emission, both in terms of the timescale and luminosity. So this nebula model here is actually consistent with the same model invoked by Brian and Ben to describe the 121102 persistent source, but simply with the magnetic energy scaled down by some fraction. And also I should point out that the free transparency timescales, so essentially the timescale for radio emission to escape through the supernova ejecta, is also consistent with our detection at about 8 years. And then on the right, we have essentially representative off-axis jet light curves. And these are all showing, possible ranges of jet energies and ISM densities that are consistent with our detection. And similarly, we find that the minimum energy required for a jet to break through the supernova ejecta is about 2 × 10⁵ ergs. And this is consistent with what we find for the models. And so this is also a viable explanation. I'll just say we are in the process of analyzing and obtaining additional data. So we do have Chandra observations at this point, which suggest a non-detection, which at least does not immediately implicate an AGN. And we do have a VLA SED, which is, I'll just say, interesting that that analysis is still ongoing. All right, so this is another example of a source that's come out of these more targeted searches. This is J1419, discovered by Law et al. And I won't say a whole lot about this other than it seems to be more consistent with a long GRB afterglow. But again, it is very analogous to the repeater persistent source, and so it could be that perhaps this is an analog of that event. And finally, I just want to come back to the radial luminosity plot from before, now adding PTF-10HGI and the range of luminosities for J1419, just to emphasize that right here they're about an order of magnitude fainter than the repeater's persistent radio source. So suggesting there really may be, if these events are related to FRBs, there really may be this wide range of luminosities. And again, this emphasizes the need for deeper radio observations. Okay, so in the last minute and a half, I just want to say a few words about our recent work. And so this is really along the vein of what I've been talking about, and I think it's interesting for the FRB community to think about. And so this was motivated by the recent discovery of 20 compact radio sources in dwarf galaxies. This was a study by Amy Rines et al. And so in the original paper, the authors showed that the properties of these radio sources are inconsistent with star formation or radio supernova. And instead, they attribute the emission to accreting black holes that have wandered from the centers of their host galaxies. Of course, this combination of compact radio sources in dwarf galaxies is really interesting to us in light of the first repeater. And so what we wanted to do is sort of compare these properties to the first repeating event and see if they could perhaps be analogs of that event. And so what we do in that work is we essentially compare a wide range of properties, and we find that they are largely consistent, not only with the first repeater, but the other host localizations that we have, and also these two potentially related systems that I talked about. And so here I'm showing the same plot as before, but now we have the offsets for all of the Rines et al. Sources. And so this fact that essentially, you have these radio sources, these compact radio sources in dwarf galaxies, perhaps they are analogs of the repeater. I'm not going to spend too much time talking about the models, but we do find that, in fact, the luminosities of the radio sources and the inferred timescales are consistent with both these magnetard nebula models that we've heard a lot about, and also the expectation for off-axis jets. And so I do think these are really interesting sources, and if we want to talk more about targeted follow-up or searches for FRBs, this might be an area where that could be interesting. But okay, so just to summarize, I think that as we start to build up our sample of FRB hosts, we can, of course, compare their properties to the distributions for existing transients. I think, as I said, the mass distributions seem perhaps inconsistent with superluminous supernovae, but it's also a little too early to be making definitive conclusions. In terms of the more local environments, I don't really think we fully understand the range of multi-wavelength counterparts. And in the radio, we definitely do need deeper radio limits to rule out the presence of associated counterparts. And finally, despite the fact that the rate of FRB localizations is really ramping up, I do think this targeted approach for looking for FRBs can still be useful, since this will immediately tell you about the progenitor. And so at this stage, I think even as we get more and more localizations, that's not going to tell us everything we need to know about what could be producing FRBs. And I'll end there. Thank you.